Okay, so before we did the conservation of mass using control volume, and I'll use the same techniques, we're just going to now conserve momentum. When momentum, well, not conserve it, but we're going to say it's equal to some forces. So two-dimensional is always easy to do, and you can extend these methods to three-dimensional, and it's always sort of the same thing where Newton's second law, right, force is equal to the time rate of change of momentum, right, momentum being mass times velocity. Okay, so this is going to be my, let's say, control volume I have, and it has momentum inside of it, let's say, and then there's also maybe a flux happening on the surface around it, like this. So there's fluxes of momentum in and out. It sounds weird to think about momentum fluxing through a surface, but it can happen. It all works out. So you do the same thing where you have these forces, and then you have that time rate of change of momentum, but write this now as an integral, and you get the same relationship where you have, well, I'm going to have the time rate of change of momentum inside of it, which is the whole, right, rho velocity dv. Notice this is really the only extra term we had, right, as opposed to the mass. And then, again, now have another velocity term right there. Before we had mass being transported by a velocity amount, and now there's an extra term right here or an extra velocity. So you can push this thing on the inside, just like this. And then same idea where we change this surface integral to a volume integral by invoking the divergence theorem. Just says you take the integrand, which is really this part right here, and then you take the divergence, which is this vector operator dotted with the term, change it to a dv, and then you have that same idea right here, where now you have a full integral just like this. And get another one over there. Just like that. So then, still haven't actually dealt with the forces on the left-hand side, and that's that like 9-term thing you deal with. But in your book, you do the exact same process, only all they're doing is they're now going to write another integral that's also a volume integral, and then they connect those things together, and then you get the equation. You can say that's non-zero, so that means whatever the big term inside has to be 0. But you should realize that all you're saying is still the same material derivatives thing has to be true for this. So that's just an overview of what these control volume derivations are getting at usually. It's you have the time rate of change on the inside and then flux terms, and then you have to redo all that analysis for forces on this left-hand side, except you're thinking about integrating the surface over an area.